Right. One, two, three. Say Gaia. 1, 2, 3. I hope if someone could check our YouTube stream if we are being there or not. So otherwise we don't start. I hope we are live now and people can see us. Will you come forward? So I think we are on the screen somewhere there. Okay, that's the camera. Right. So I assume we can start. So welcome. This microphone is weird sounds, but I hope we can be heard. So welcome to the 13th workshop in a row. We've been doing them uninterruptedly over the last 13 years. We started in 2010 in Cambridge, and then we traveled around Europe mostly. We ended up in this sunny Sardinia, sorry. We've been to Sicily already. Emilio Molinari is here. He's our main host, official host here. He's director of the observatory here. Emilio, say a few words.
Welcome. Good morning. Good morning. Good morning also to the camera. Welcome for this meeting that we are having here in our region. We are one of the southernmost region of the Union, and we are happy to be part of this. So it has been a pleasure and also a duty, an honor to host a meeting which is coming from a European project. We have always been part of this since 13 years or maybe more. And so welcome to Sardinia. And I hope you will enjoy also the visit to the radio telescope, because the observatory in North Cagliari, which is part of the Italian National Institute for Astrophysics, manage one of the biggest antennas radio telescope, which is located north from here, and we have also planned a visit this week. So welcome again, and let's start with the real work now. Enough with the words. Thank you.
Thank you, Emilio. So a couple of technical announcements. So the technical announcements are like that we are on Zoom all the time. There's just one Zoom link all the time. And to people here in the audience, if you do want to present from your own laptop, you can do that, but you have to call in to the Zoom meeting, then mute everything, cancel all the sounds, and then you can present it from here, and then we will be seeing it on the screen. But remember, this will be going through Zoom server, so there will be some delay. Yeah, another alternative that is that you send me your slides, and then my laptop is connected to the screen and to the Zoom, and it goes both to here and to YouTube channel and so on. So please use the microphones when you speak, and when you ask questions as well. There's another mic in the room. The same, so raise your hand, physical hand or virtual hand if you're on Zoom, so that we see that you want to ask a question. So I hope this is all technical piece I had to say about. So I let Monika take the chair of this first session until the lunch break, and enjoy. Yours. Stand somewhere. Okay, just get the little ring thing. Yes.
Okay, so our first lecture is by Gerry Gilmore from Cambridge. You have half an hour, including the questions. I will show you 5 minutes earlier that it's coming to the end. So enjoy, and I hope that you will have a lot of questions after the presentation. Enjoy.
Thank you. Good morning, everybody. So that's what you're thinking of me, really.
White noise.
Okay. White noise. Yeah. So rather than quick questions after the presentation, normal style. This presentation is the question session. And so let me explain exactly where we're at. As you know, this is the 13th of these meetings, and they've been embedded in an EC-funded program, which was called Optical Infrared Coordination Network. It started about 25 years ago now, and it's been quietly running along in the background and providing the resources to do quite a lot of technological development and quite a lot of networking development. And so Opticon sponsored a lot of the development of what has become the adaptopics community across Europe. So much of the technology development and still is. Opticon was involved in building about a third of the SPHERE instrument on VLT, the world's finest exoplanet facility still. And Opticon was the original primary sponsor of what has become the ELT, European Large Telescope. So it's done lots of community-wide things. In the background, one of the things that we were working on developing was time domain astronomy. And so these things, these workshops are one part of a sequence that has been in place for a long time to develop that. And as always, with a subject like this, there's the people who actually do the work, and the people who write the code, and there's the people who do the science, and the people from it. Somewhere in the background, there's somebody who's been finding the money to allow it to happen. And that's something that you don't notice normally if you're lucky, and it just sort of goes on. And until quite recently, it has been a relatively straightforward process, because the European Commission was enthusiastic about developing growing contacts across Europe between all the different countries. But now that has started to change in two ways, and in two these terms. Yeah, sorry. Yeah, oops, I think you've got. Okay, right. And so the system is changing. Therefore, to keep the infrastructure in place, somebody has the microphone turned on. Yeah. Right, you've muted everybody. Good. And so the next cycle in this 5-year renewal program is just starting. And for that, this time around, we need a lot more help from you than has been required previously. So this isn't just a usual sort of political nonsense. This is something where you have to actually provide some information to support your own futures. Now that seems a self-evidently obvious thing too, but nonetheless it has to be done. And the reason being is that the European Commission is changing the way it operates. Partly this is of course because of the fault of the United Kingdom and Brexit, and this has disrupted the normal communications flows. But also it's the big political change from the normal framework program that's been running for half a century almost into what is now called Horizon Europe. Horizon Europe is targeted on specific goals. So instead of saying, yeah, we want Europeans to work together, instead of saying, we want you to do something that you're good at, don't really mind what it is, as long as you're good at it, they now have targets, and goals, and ambitions. It's the targets are a little bit out of date, actually, unfortunately, because they were determined before COVID and before inflation and before, of course, energy crisis. And so they're targeting things that are almost luxuries, some of them by now, but nonetheless, the structure of the community is changing. And so there's a completely new political team in place and a completely new administrative team in place that split away the people that we used to work with. One feature of this is that in 2 weeks' time, the new presidency of the commission is running a big meeting that we will be trying to talk to commissions at, and that's in Brno in the Czech Republic. The Czech Republic, of course, is part of what we're doing here. So this is an example of where an individual who happens to work in the Czech Republic can have a disproportionate positive effect because they want their things to succeed. Anyway, the gist of it is is that currently there are several new initiatives going on for largely reasons we don't really understand. The Commission said our next big initiative is going to be a combination between astroparticle physics and astronomy. This is an initiative, I think, that was motivated by the astroparticle physicists. No one seems to have talked to anybody in astronomy. It's quite late in the day already. And these discussions are really just starting. In fact, I'll be on a teleconference all through your lunch break as part of that. But the astroparticle people, their motivation is multi-messenger astronomy, quite reasonably, really exciting and so on. As you know, there are 2 or 3 multi-messenger events that have happened over the last few decades. Supernova 1978 was the first of them. Was the gravity wave 17, and there's been one more neutrino event since that's been identified. But unfortunately, 3 events over 40 or 50 years isn't enough to actually support a whole program. And so what the program is rapidly evolving into is time domain astronomy, i.e. what you guys do. And so the astroparticle community is putting together a proposal which would allow them to take management control of time domain astronomy. And so they would tell you what to do, they would schedule your runs, they would organize it all for you. And I know for a fact that none of you has been asked about this, because we didn't even know about it until very recently, and it's all changing on an hourly basis. But nonetheless, this is direct impact on this community and on you. That's why I'm talking about it now. So to make sure this doesn't all go the wrong way, and it doesn't just destroy what is actually a functioning working system by well-meaning, enthusiastic people, but people who come in from an utterly different background, don't use ground-based telescopes, they don't do what we call time domain astronomy, they do high-energy alerts and so on, and the brokers. I need to get some feedback from you. And then there is different groups of people competing for the same budget. That's not too critical. That's always the way. We just have to write a good case. And so there's a bunch of questions that I'm now going to go through. And I know what it's like when somebody just stands up front and says, answer my question now. No one will. So really what I want you to do is think about these questions and send an email. You can send it to Lukasz, or if you know my email, send it to me. That's fine. Doesn't matter. But do respond to these questions because what we need is real stories from real human beings. Now, when I go and talk to the Commission, they know perfectly well I'm not a normal human being, because normal human beings don't get to talk. But normal human beings are people like you who actually do work, whose careers depend on it, whose futures depend on it, whose local communities at your university depend on having this resource, being part of the time domain network. Those are the stories we need. We need to say, I work at this university in this country, and we work as part of this time domain network. We weren't part of any big European project before, now we are, and we want to continue. So that's the sort of information that's needed, and that will be the case for continuing EC support. So I'll just run through some of the sort of more formal questions. Many of these will mean nothing to you. You don't have to note all of them. If you see a question which you think that you can contribute to in any way at all, then make a note of it and respond. And so just running down, this is the sort of level that what we're trying to do. So the way in which the community has expanded in Europe, one of the things that the Commission's always been keen on is new users, get new people involved. And so by marketing access to 4-meter class telescopes, we weren't very successful getting large numbers of new users. There were a few, but not very many. The thing that really worked was the approach that Lukasz has taken with time domain astronomy, of saying, no, we don't want you to come use our telescope. We want you to put your telescope into our network. And then everybody benefits. You are part of the network, you are part of us, and our network is bigger and better than it would have been before. And so those are examples we need of all those individual cases. The EVN is another example. The radio astronomers are terribly good at going around and linking an extra antenna into the EVN, and they have an absolutely wonderful program running through Africa, which they upgrade old telecoms dishes. And people get locally then to be really part of a state-of-the-art program, and it's really great. And so this is my line there about contributors, not takers. And so this is, I need case examples from you where your facility has joined Lukasz's network, and you said, yeah, we had this little telescope here, and we may have used it, or we may have done student work with it. Now our little local telescope is part of a cutting-edge international thing, and we're proud of that. So 70 things like that. Similarly, anything, the jargon is raising the local skill base. That means if you've ended up with some money so you can employ somebody. So if there are any jobs that have become available, like you, for example, say, right, I now work on this telescope and my university now funds me to do it, whereas previously they were short. You need examples like that. Similarly, well, the technical thing there is building on local capital. I mean, most of these cases, the telescopes come in, we're not paying for a new telescope, we're paying to upgrade something that exists. That upgrade gives value distributed across the whole of Europe, across lots of countries. And then there are other specialist things like virtual access to survey data, reusing archives and so on. You benefit from that. So then one of the things the EC said is, right, we don't want to talk to so many people. We find it administratively inconvenient to actually talk to the people who live in Europe, so we're not going to do that anymore. We're going to, what we want is to have a small number of representatives of very large communities, rather the way the national organisations work. Here in Italy, there's INAF. There's a national organisation. You want to talk to Italy, you know who you're going to talk to. Whereas in Europe, you don't have that. So they're trying to change it, make it simpler. So instead of every single organisation being a named partner in every contract, and hundreds of people having to sign things, they want to make it a bit simpler. And nobody knows how to do this. ORP, the Opticon Radio Net Pilot, it's called a pilot because it was a first attempt to do this. They said, okay, here are two big communities. You go together and you become one community, and then we've only got one community to talk to, and that's obviously simpler for us. Now, to some extent, that puts all the pressure on us at the bottom end to try and work together. To some extent, it works, some extent it doesn't. And it's one of the things we have to do is decide whether or not all has actually worked, or whether it's just two communities carrying on in a slightly smaller budget than they were before. So if what would be very, very desirable is any examples, if there are any, there might not be any, of real synergies between optical and radio. The only one I know of is actually Emilio here, who actually runs an optical and a radio telescope, which is, I think he's unique on the planet, but doing that, perhaps he's not. There might be somebody else. But if there's anybody, any case you know of, where you have ended up talking to radio astronomers, I would imagine that Poland has got to be the best possible case of that. You're a rather integrated community, and you do work across radio optically. So give me some examples of real cases where, is there a paper that you've written together, or a student you've jointly supervised or something? Arga is probably online, she might be able to give us some examples as well. But that's what we need, is real world cases saying, yeah, this works. And there is some benefit. And then there's the question of, well, what comes next? So the jargon in the middle there, DM is dark matter, DE is dark energy, and MMA is multi-messenger astronomy. That's the astro communities. Now, that tends to be a very, very different community from the rest of us, largely because no one knows how to observe dark energy. No one knows how to observe dark matter. And the multi-messenger is something that's really going to develop fast in the future. But it's been rather small scale in terms of number of events, low latency is the jargon up until now. But is this the sort of thing which you hope to be involved in? Will it be advantageous to be connected to this community because you're interested in what they do? Or is it sort of different from what you're actually interested in? But we need to know examples again, so that we can then just help to decide, well, which communities would it be sensible to put together? From the sort of top level of the commission, they can't tell the difference between astronomers who study asteroids and astronomers who study dark energy. But that's beneath their resolution limit. And yet, from our perspective, these are totally different people, totally different techniques. So we need examples, we need counter examples of what you can do and what you can't do. It's also true, that point I made at the bottom there, communities are not stable fixed groupings, so you don't have to sign up to do one thing for the rest of your life. You can say, I'm actually interested in 10 different things. And that's great, because that will lead to a much broader community, or not, as the case may be. Then the bottom line there, that's really the key, is in what ways have you actually benefited from being involved in the ORP program, travel and systems? Has our resource helped you come to a meeting like this, for example? And it must have done. Spending the money on something, you're going somewhere. But we need a few examples. We can go into our reports and, yeah, well, these meetings are fantastic, and they allowed us, our community in this country was able to meet people from other countries. And we can say that generically, but we need a couple of real world examples, real names, real numbers. Right. Did I press that button? No, I didn't, obviously. Wrong button. I ruined it. What did I do? Right, okay, now it's changed. I'm afraid this technology is too sophisticated. Okay. A button is more than I can manage. So, okay, so the next thing is about widening access. So we need some comment and feedback on this stuff. And as I mentioned earlier, the most effective way in which access has been widened is by linking extra local communities into the bigger community. And this is really key, I think, for us. It's the one thing that we can really look back and say, well, look, when I was working in astronomy in the UK 40 years ago, I had no contact with Central Europeans at all. I spent all my time in the US. And now look how it's changed. It was definitely for the better. And so all these different communities and countries, how many different communities and countries are there that are now involved in the ORP time domain astronomy, which were not and would not be apart from our support? So that's really key. Are you here because you're part of this community, or are you here because you will be here anyway? That's a key thing for which we need. Then there's the under-supported science communities, people who don't have enough money to be critical mass on their own right. If you know of cases like this, and there are many, they're usually university observatories, where these people say, yeah, we don't have enough money to actually fund a state-of-the-art telescope or a state-of-the-art instrumentation suite, but we can share with you. And again, real examples of what's needed, not just talking on. So these other points I think I've already made. And so I'll go on to my last on that one. That's great. No, I've gone back one. Okay. Oops. Too complicated. Right. Okay. So this is the key. The key slide. Sorry, I've got it out of order. The way. The other feature that the EC says is that, oh, well, we've got over 100 access type contracts running. And new communities keep coming along and saying, we want one of these too. And they can't just keep expanding because they have a limited budget. So they say, right, so if you have been benefiting from access for a long time, prove to us that you still need it. And there are a variety of interesting terms that come up, which mean reducing the money. One is called co-funding. Co-funding is a way of saying that somebody else is going to give you the money, not us. And so we've been asked to find where else would the money come from, the money to support transnational access. No one has yet managed to come up with an idea because there isn't a huge supply. Now that's not true in all communities, but some communities, industry is able to help with things that are more near market, more profitable and so on, but we do basic science. In basic science, there is no other source of money except national government money. The other way they're talking about doing it is by giving you a fixed sum of money on day one and say this is your budget for the next 4 years or 5 years. This is a slightly more technical point, but this has been a pretty obvious way to do things for the last 20 years. But suddenly we all have high inflation. And so if inflation carries on as it is, then you've got a fixed budget, you've got a fixed cash budget. In 4 years' time, you've only got half of value of your cash. So do you lose half your staff, or how do you manage it? So if any of you are involved in the administrative side of things and had to deal with things like that, then please send us a note, a comment. Then talking to the people who run the infrastructures. And so what would happen if we didn't give you leasing money? I need to know from you how you would respond. If you have a telescope in Lukasz's time domain array, and suddenly there was no resource available to maintain your connection, would you just stop? Would you have to stop? That's what some operators would have to do. They say, sorry, we don't have money. I have to give my access to my local users. Your local might be national or whatever. I can't just give it away because those are the restrictions. Or would you still be able to carry on exactly as well? You need real world examples to say, yeah, well, actually, if you just give us a sort of minimal amount so that we can run the center, then the rest of it will be fine, or not, as the case may be. Again, real world examples are needed. And then it turns out for the bigger infrastructures, the big national facilities like SRT and so on, the access money that's provided is actually used to increase the level of support for the outside users. There's not actually enough money to run the facility at all. It's usually typically 1% of your budget, 2% of your budget. And that 1 or 2%, because it's unlimited, what you can do with it, tends to get used to support users from outside the national community who don't have access to national funds. So what that means in many of the big facilities is that you can still get access to it, but you'd have no travel money, and you'd have no one to buy your laptop, and you'd have no one to help you with the data reduction. Could you survive that situation? Yes or no? So I think for most people the answer is no, but I can't just say that on your behalf. So send an email, send a message saying, look, just this tiny bit of money, it's not a lot, but if I don't have 3,000 euros that I can spend on whatever I want, I have to get it from somewhere else. And that's what we need for the commission. That's what they're really interested in. And I think that's the real value at a human level for what we do, is that, yeah, we can give that 2,000 euros to whatever facility has it. It might be Lukasz's system, or it might be some other telescope somewhere that you want to go and use. But if they didn't have that money, then you would have to manage it yourself. And that's particularly for a telescope in Chile or somewhere, that's probably just impossible for most people. Just couldn't do it. So that's the bottom line, and I'll stop here. How would you be affected? That's what we need to know. Real world examples of how real world people will be affected in your facilities, your science, your students, your futures, your ambitions, the people that you know who might be interested in joining the time domain network next year. They're a smallish university that's got a smallish telescope that's actually not bad. It could be upgraded and put into the site, and they'll never have the opportunity. Because we don't know those people, we don't know that we can't say we have a growth potential, we can't make a case. So I don't know how I got on for time, Mrs. Chair. So that's, but anyway, those are the key points, and that's what we're trying to do. So the bottom line is, we in the background are quite prepared, we've always been prepared to be happy to put in the work to give you the opportunity to carry on. Most of the time, you don't even have been aware of the fact that it was there. Resources kept arriving, and you thought that was wonderful. Now I need some help to make sure that that continues. So I'll leave you with that. So if there are any questions, I'm happy to take them. Any suggestions. But, I hope that suitably long and gloomy list of questions is what I got across. Thank you.
Any questions? Connor, I'll give you the microphone.
Thank you. So actually, that's a very open question, but EC is very sensitive on also this SSD, so space surveillance tracking, space equational awareness issues, and they have like also some projects going on that. Is it somehow beneficial to use the astronomical research infrastructure that we are using for those purposes? I know that data reduction tracking is different, but maybe it's somehow like something that like join, at least in the proposal phase, and maybe that could help. You comment on that.
Yeah, that's there are the two interests. It's a very important point. And this links to the boundaries between our community and other applications. We think of ourselves mostly as a basic science, just trying to understand the meaning of existence and so on. But actually, there are a lot of applied science applications at our boundaries, one of which is the space situational awareness and so on. Another is very high bandwidth communication in ground space, in which telescopes with adaptive optics and lasers are used, the same as we do. And all of these applications are enormously important because that is our connection to the money-making, the commercial side of society. Just every few years, there's a big upgrade, and the ESO one was finished just last year. It's a book of 400 pages thick of all of the societal spin-offs and benefits from what we do and the connections, like the one you've made. And these things are really important because they show that we aren't a community which is exciting young people and doing wonderful things, but basically we're a cost to society. We're actually a benefit to society in a material sense as well as in a cultural and intellectual sense. And so yes, examples like that are really important. And the SSD is a particularly valuable one, as is the communications one. And one that we've used so much that it's lost its novelty value is the fact that medical applications of adaptive optics. I don't know if you know, but if you ever get laser surgery on your eye, the technical term that the surgeons use for the laser spot on your eye is a guide star. And they just took over our jargon and our technology, our software. So that's a nice practical application. But the more of those, the better, because we're not just a drain. We're actually contributing something valuable to society at large.
Okay, any more questions? You have a lot of questions on the presentation, so maybe some answers. Okay, so thank you very much one more time, and I hope that you will get your answers later during the coffee break, maybe. Thank you. So now we have second presentation today with Emilio. Please join us. You already know Emilio from the beginning.
Yes, of course. Thank you. Good morning again. And I could not say no to the invitation to give a talk because of course we are hosting the workshop. So I want to just to give you an example of how it is difficult to join two different communities because here I am managing two telescopes. Two telescopes. Yes, one is the Sardinia radio telescopes here in managed by Observatory in Cagliari. It's a radio telescope, 60 meters by 64 meters diameter, and looking at a wavelength of looking or listening or whatever, recording the data at a window 1 centimeter lower and a bit more. And the other one is the REM, which is a very small telescope, robotic telescope in the Chilean Andes. It is 60 centimeter, but looking at 1 micron, it is visible and infrared. What is just a small presentation of both. REM is a fast-moving telescope. It's a robotic one. It is not managed by anyone. Just it is doing things by itself. We have an infrared camera, a small field of view 10 by 10 arc minutes, and an old, I would say, infrared chip, which has only 500 squared pixels. The same is we have visible imaging camera that they are looking at the sky simultaneously. So we can observe and record at 5 frames simultaneously, 4 in the visible band, G, I, and Z, which are split by a series of dichroics, and 1 of the infrared channel, J, H, K forward. So it is very interesting to have data in different bands at the same time. This is the dome in the La premises of ESO, and an example of images of the same nebula taken by the 2 cameras, and then combined in a color way. Yes, this is how the things is working on the REM telescope. You see, there is a OS, an observing software, which is managing all the other subsystems. All the systems are connected by a messaging system, but they are working in their own way, or even in their own machine. So I want to how it is working. It's a dynamic scheduling. Every time an observation is made or an input is sent to the telescope, the schedule is changing. The schedule, well, of course, it is looking if it is a GRB. GRB is the main reason this telescope was built, and now GRB is a paradigm of target of opportunity. When a GRB comes, and here it is coming directly from the GCN alerts, everything is stopped and the telescope points to the GRB. So it's a way to override anything the telescope is doing. What is doing otherwise? It is a list of observing program from Italian allocation committee and also from the optical allocation committee. And to the scope of this black hole TOM things, this is actually how it is working. At the end, we send a single command to the telescope, send entry, and then it's giving the target and the coordinates, and then it's doing by itself, taking on priorities, and so building a new schedule every time something is observed or received. This is the main entry point for anything from outside that can devise in this framework of real world. REM is also observing standard stars every night, so it is able to do automatic monitoring of the performance. You see here the 0 point as calculated autonomously, and every night these big jumps are the washing of the mirrors. Not only GRBs, we are looking also in programs of monitoring, like lasers monitoring here on the right. On the left, the transient phenomena that we are looking for. This is the 1987, 2017 supernova, kilonova given by after the gravitational wave. So we could see in calls the kilonova, which is on the right with the REM images. How do we monitor this? We have a thermometer, which is a public page that you can all look. You see on the right a piece of this. You see the heaven above the telescope, which all the target list that is going to observe on the right, and anything giving status of the domes, temperatures, pressures that are also a source of alerts when anything is not working. This is also could be also an output that could feed information to a public page for having the schedule of what is planning to do. All the data are sent almost immediately to an archive in Bologna, where the owner, the PI of the program, and after 1 year, everybody can download images, and where they are immediately available, together with some bias stars and flat fields to do proper data processing. It is unsupervised process, so I understand that something can go wrong. Out of focus images, not good pointing, or stray light from the moon. This has to be dealt with by a human intervention. So it's not a complete sequence of science already. Still, there is something to do. The other side, the other wavelength, these are the Italian radio telescopes. INAF manages 3 single dish telescopes, 3 antennas. One is here in Sardinia, 64 meters diameter, and the other 2 are in Sicily and near Bologna, Noto and Medicina. The radio telescope, Sardinia telescope, is participating in the ORP program. Still, it is ongoing. It has a major, you will see the major upgrade program ongoing, so it's not observing now, but it will in, say, 1 year from now, and then it will be an opportunity to be used by ORP programs as a single dish antenna. Also, it has participated, and it is and will be participating to the other data producer for ORP, which is the EVN that was mentioned just before. Well, this is the few data on the antenna. It is an active surface. It is built by thousands of panels that you see on the right, and that are slightly movable in order to have always the active octave perfect shape. We have now 2 receivers working. Well, not working because we are doing the job, but LP band and K band, LP 1 pixel receiver and K band 7 pixel receiver. This is a very big difference between CCD and radio astronomy. But we are upgrading, as I told you. You see the band in yellow that are already installed, that has always been working, and the 2 that we are building in-house, the S band and the C low band. And thanks to the European money for the big project, say almost 20 million euros, we are renewing all the shape and building new receivers that will exploit the capabilities of the antenna, which is a very smooth surface and can observe up to or down to 3 millimeters, so more than 100 gigahertz. This will be hopefully ready in 1 year from now, ready and running. This is the project. In fact, these are all the receivers and upgrades that we are going to do, from bolometric cameras to spectrograph. And this is the status. You see, almost half of this is installed or delivered. Of course, we had many problems due to the COVID lockdowns and consequent delivery of materials and computers also. So what is not in blue here, it's because we are running, and we are really running every day to cope with all these delays that this couple of last years had for us and for everybody. This is how it is working. On the right, you see the 7-pixel or the new cameras that we are building. That is the sky coverage. It is really undersampled. So in order to have images or accounts for measures of sources, we have to do to move the telescope and to do mapping on the fly. We can do on the fly mapping so that we do not stop recording the input from the telescope while we are moving the telescope right and left and possibly also up and down. And this is how we do map and compute the flux of the objects. And this is how we will do, even we will have much more pixels in the future. One of the camera will have also 400 pixels, but you see the coverage cannot be continuous. The pixels are separated on the sky because the fields are packed together on the focal plane. But we can do monitoring even more efficiently than with optical because we can work 24 hours and 7 days per week. So that, okay, you don't see here really very well the pictures, but on the upper right, you see in the dark blue time span when an object can be seen by optical telescopes, and on the left, when it is visible from a radio telescope. Basically, every moment that it is above the horizon, we do not fear the presence of the sun. So this is an improvement on monitoring that we can offer with radio telescopes, monitoring and also time domain astronomy reacting to transit alerts. This is one of the input that we can have the red arrow. How can we hopefully react to alerts? We need more or less half an hour to set up the telescope. And then every 30 seconds you can do a cross scan and they have a measure. This is a cross scan, say, one you have centered the object, you cross on the object and measure the flux in this way, provided that you have a nearby calibrator for pointing and flux calibration. But still, we are in a process, in a phase that human intervention is needed in almost every phase of this. Scheduling, setup, observing, you can do it manually, even if after the lockdown, we are able now to offer the possibility to do this from remote. So it has been an improvement that we learned from these last 2 years, that when we never stop observing. And data processing is still in, I would say, pilot moment. They are not science ready at all automatically. So human intervention is a heavy process in this last step. But okay, I'll conclude here. I've shown you what we can do, what we will do in the future for participating in this joint project. We have already been participating. REM has already observed optical and now ORP program. SRP has always participated in EGN, and we will in a single dish in the future. What are the problems for Gerry? Are we able to run both these with less money from the European? Are we able to offer a homogeneous data products to all the scientists that do not have the possibility or the capability or the time to process radio data and infrared data when an object is needed? The problem is not really the money. Problem is always people. With the European money, we cannot hire people, and we need people to do all the things that the human intervention is needed. I said that we can observe 24/7. It could be true if we had people enough. We do not. Writing automatic data reduction for infrared, visible, and radio is of course possible. We do not have the people to do it. So the real improvement of all this would be having more people. And in this way, if we could reorient the intervention of the European community to help on this side, would be really great step forward. Thank you very much.
Great. So, do we have any questions from the lecture room? Raise your hands. Please.
Hi, thank you for the.
You have to put it close.
Does it work?
Yes.
Okay. Is there any prospect, you think, for monitoring or following Gaia's speed of view simultaneously, the instrument, rather than trying to do a triggered follow-up? What about trying to track simultaneously? I understand scanning law is very different to what you can see, but maybe parts of it be achieved.
You mean while Gaia is observing?
Yeah.
We had, not with Gaia, but with other telescopes, we have simultaneous observing that we can schedule, and we had scheduled. Last time, just to mention a method, we had a common program with the James Webb telescope, with the REM telescope, with the 6 centimeter, and unfortunately, James Webb did not point it where it was to be pointed. So, and in Chile, on the other side, in Paraná, the weather was not good. So the only observation that they had for this program, they are with a 60 centimeter of REM, which is okay. But we, of course, we do it.
And in the radio.
And in the radio, yes, of course, as we are already doing a joint observation with all other antennas for the EVN and the global with the LVI. It is of course possible to do with other kind of observatories, space-based or ground-based. Problem is scheduling and the conflict of schedules, but that is for everything. But very, very open to do it, as we did.
Okay, any questions from the lecture room? Or we have some on Zoom? Zoom people as well can ask questions. So, nobody? Okay, so thank you very much. And the third lecture today is Simon Hodgkin from Cambridge. And after Simon, we have coffee break. So I hope you will get more energy after the coffee. But during the Simon talk, yes, as well, focus properly, Zoom as well.
Can you hear me okay?
That's the magic point.
You have the pointing arms.
You know, I haven't seen this for years. And I really miss your magic.
It's amazing.
Pointing stick thing. Ring.
Magic ring.
Okay, it works.
Okay.
Hi, everyone. It is a pleasure to see other human beings in 3 dimensions. It's been a very, very long time. And thank you very much to the organizers, to the hosts, to the funders, and to all of you to give me this chance, and to everybody on YouTube as well. So I'm just going to give a kind of summary of where we've got to and what is the status of the Gaia Science Alerts right now. And looking ahead, we still have a future. And so I'm going to try and encourage you to stay connected, keep talking, and work with us, and we get the most out of this satellite this mission we can. And the transient is part of this. So everything I'm going to talk about is preceded by this paper. So this paper is over a year old now. So in there's a lot of technical details and information on our systems and our methods. So please, if you have questions, talk to me first, but also go and have a look at the paper. I'm here until Thursday. So, but I give you that as a reference. I know not everyone here has seen previous talks, and there are new people. So I'm going to go through some of the basic sort of backgrounds to the Gaia alerts, but for the nitty-gritty details, go and look at this paper which summarizes the Gaia transient survey. I only pushed it once. Honest. Okay, we do have changes in Cambridge, and this last couple of years has been tough. We've been running in a very much reduced capacity. Funding has this magic habit of drying up, and people have this need to move on to better paid and more permanent projects. So one of our key developers, Abdullah, he's left us now. He's still helping us in his spare time, but he's left the Gaia Alerts project to go and work on something involving human health and happiness and well-being, much more important. However, he's still going to help us with the final bit, which I'll talk about at the end. We still have the crack team of Diana, Elme, Susanna, myself, not so much crack, and for the eyeballing and advice and the operations and making sure we keep running, because we kept running continuously since the start of the mission. So since our first alerts in the autumn of 2014, these people, for the most part, have kept us going. And then there's many people in the room who help with the eyeballing as well. The eyeballers are going to be replaced. You'll hear about that. We have Guy Rickson, who went to work on other things, but now he's stepping in to take over some of the responsibilities that Abdullah had for making our systems work. So Guy's still part of the picture. And then Gabor is the evil genius who's going to make us redundant and is replacing us all with robots. So Gabor, I know some of you have seen him talk in the past. His paper is in preparation. His machine should be switched on today or tomorrow. And it's been running for a while in the background, nobody knows. But what we're going to do is expose it to the world. So the machine is ready to go. Someone has important text message. Okay, so our detector is, in a sense, very simple, but we overcomplicate it. But the way to think of it is this. We either have something that's new to Gaia, or it was already there and it changed status. And in changed status means it got brighter or it got fainter. And it needed to get brighter by a significant amount, which is a magnitude, or fainter by a magnitude, or it's allowed to change by a small amount, but only if it was historically stable. So we have this old source mean RMS detector for that case. And we have the delta mag detector for the high amplitude variables. So we distinguish those. And then Lukasz invented and, well, readopted the Skub-von-Neumann detector to allow things to change more gradually. So if you have trendful behaviors, Skub-von-Neumann is much more sensitive to those than any of our pre-existing detectors. And then for the new sources, it's very simple. We need to have not seen it before with Gaia. It's new to Gaia. And all of these detectors, because the sky is the way the sky is, we need to have seen it twice with Gaia. And when I say the sky is, I mean to Gaia. Because the sky to Gaia is a mess. And this is not the sky to Gaia. This is cleaned up. This is after the data has been onboard, cleaned, and then sent down. So the sky looks even worse than this. And I picked the worst cases. This is near Saturn, near Sirius. But these effects go across degrees across sky. So the sky to Gaia is polluted. And the reason Gaia works so well is because every star is observed hundreds of times. And so you can solve for what's real and what's garbage. But we don't have that luxury. We have to look at sky that looks full of noise every day. And we have to do a sifting of what's garbage, reflections, spikes, artifacts in the data. And the other thing we have to deal with is on the left-hand side, is that there's source confusion. because for Gaia, we've got a lot of sources. So there are billions, as you know, in the Gaia data releases, and especially in the plane. So these sources are all very close to each other. And we have a preliminary astrometric solution, which means a given transit needs to be associated to a source. We use, for the initial data treatment, the tolerance is an arcsecond, even though our astrometry is good to 55 milliarcseconds. So this initial decision of which source the transit belongs to in the daily processing is never going to be as good as it is in the data releases. So this is why there's a difference between what we publish and what you see in the 22 months or 28 months data releases with much, much more clever processing than we can afford to do on a daily process. So all of the Gaia alerts, you have to kind of think, you just get a quick flash look at the data and then you have to make a judgment because the next lot's coming. So it's a non-trivial and fast process. And the fact humans get to do any of this is crazy. Don't let us near it. But we did okay so far. So, and just to put things in context, we have something like 10 to the 8 transits per day, measurements from the Gaia satellite every day. And this is the daily rate of these different classes of data as a function of time through the mission from start till the end of 2020, start of 2020. And then the things that we class as detections to our alerts, so they're new sources or they're old sources that change, is the blue curve. And so we can go from 10 to the 8 down to 10 to the 3, or possibly 10 to the 4. So a few thousand events per day that we would classify ideally as transient events. Something got brighter, something got fainter, something appeared. Okay, but eyeballs can't look at a few thousand per day. That's not helpful. So we have another layer of filtering, which mostly takes the account of the environment of the source to throw away the obvious garbage. So the humans only have to eyeball this red curve, which is tens of events per day. And we can cope with that. Like we can do that in a day, okay, with our team. And then the numbers of alerts we're publishing each day is gently rising. And so now we're approaching 12, what we think are very pure transient events per day from those different classes of detectors. And the filters, I won't spend a lot of time on, but essentially the things we have to deal with in our daily processing is handling things that are either in the wings of a bright star, or they can be far away from a bright star but lined up with a bright star, or near a minor planet, or near a major planet, or near a moon of a major planet, or just have a neighbor, if something's lined up with a neighbor in the wrong direction. For Gaia, it's fine, you'll get it again the next time, but for transient detection, all of this is a real pain. And so we have classifiers and rejections to handle these classes, and also things that are already classified and known to be periodic variable stars. So we need to remove those as well, because they're not urgent and there are better systems to manage those. The photometry we're producing for you is roughly 1% good at the bright end. The calibration is good to 1%. And at the faint end, 19th, it's about 3%. So this is the precision of the photometry. And that precision is measured by repeat measurements of the same star, so we can test our internal calibration. Our calibration is predictive. We base it on the history of everything measured by Gaia. So the assumption here is that Gaia won't change, it will be stable. So the calibration is not contemporaneous with the measurements of the data. It's predictive calibration. So far, it works very well, and we're happy with it. So we just hope the satellite continues to operate as it has been doing very well in the same way for the future going forward. We update it roughly monthly. That's slowed down a little bit now because the data processing center in Cambridge are currently undergoing their cycle 4 processing. So we're back in the queue for the next data Gaia data release, more important than us, but hopefully we'll update the calibration soon. And the astrometry is exquisite. So we see a large fraction of the transients that all the other surveys find, like ZTF, pan-stars, as long as they're bright enough for Gaia, but we don't necessarily see them first. But what we do get is astrometry good to 55 milliarcseconds for them. So every transient that we see as well, we will give the best coordinates for. So we become the benchmark coordinate measurement for every transient that we can see. And the transient name server updates all the coordinates to the Gaia coordinates when we see them. So we're at 21,000 published alerts so far, which is, I can't believe we're still talking about these things. So just 8 years. So it's remarkable that this system has been running since, and Lukasz was one of the original designers of this, also started these meetings before we even had a satellite in space. So I'm very happy we're still here, still talking about these things and still publishing with us. So we're in the regime which is now reaching 12 per day. And these different regimes and described in the paper are where we brought different detectors online, where we improved our filtering. And mostly it was learning how to filter out the garbage that meant we could find the transients. So it's that distinction that really won the battle. And what's special about Gaia? I think I skipped a slide. Yeah. Here we go. So many things special about Gaia, but where we're just different, really different to these other surveys, is we're all sky. And so these are galactic coordinates. And so you can see the Gaia has got this beautiful collection of galactic plane transients, but the only other survey that can see them is the Saturn. The other surveys avoid the plane. It's too confused, too crowded. And a Saturn is a bright limiting survey. So if you want to see fainter things towards the galactic plane, then Gaia is your go-to survey. And what we see when you look at the fraction of classified versus unclassified Gaia transients, and by classified I mean spectroscopic, or they have a good model fit to a microlensing for events, so we have confidence, then the classified ones are uniformly distributed in the sky. It doesn't matter where you are. But it's the unclassified ones, the ones we don't really know what they are, dominated by the galactic plane. So most of, or another way of thinking about this, is the majority of things that are in the galactic plane remain unclassified. So we have a disconnect here. And we can think about why that is, but we suspect that what's really happening is the supernova surveys, the TDE surveys, the AGN surveys are all already classified. People chase those. But in the galactic plane, it's a little unloved. And some of the most interesting science is happening there. And there is where I would argue we could focus a bit more attention and energy. And indeed, in the paper I showed right at the beginning, then Elme and Thomas came up with a classifier to say, well, can I tell a CB away from a young stellar object? And solely based on the use of a parallax, a color, and a G-band magnitude, they argued that you can, and you can do a good discrimination in this HR diagram between at least these two classes of transient. And so that figure there is, I think, quite inspiring. And we could be following these up, and I know Elme is involved in programs to follow these up and demonstrate that these machine learning classifiers can help. But that used very limited parameters. So I'm gonna, if I've got time, find the right button. I'm gonna go on a little walk through the data to sort of show an avenue I want to explore and show you how rich I think this data could be. So I'm going to talk about parallax. Parallax is the first thing. So now we have DR3, and we will have DR4 in a couple of years. I think end 2025, no earlier than end 2025. And we've been finding amazing events, and we're going to hear talks about some of the really, really exciting classes of transients that have been found by people in this room, explored by people in this room. But now we have DR3, and I'm sure some of you are going to talk about the impact of DR3. And I think having Gaia transients with Gaia multi-dimensional data is going to shed a lot of light on this problem of having 72% of our transients unclassified. And so I think we can do a lot about this. So for the first thing, I was looking at the impact of parallax, which is what Elme and Thomas were doing earlier. So I'm just taking 2 sigma or better detections. I could play it as a movie, but I won't. So these are things that we already classified as CVs, and as Thomas and Elme showed, that essentially they do sit in the space between the main sequence and the white dwarf sequence. And the size of the circle here is the amplitude of the event, so a scale for the amplitude. And so already, if you have an object with a parallax, you can stick it on there and be fairly confident you know what it is. It's going to be a CV. Except novae kind of sit a little bit in the same space. So it's not quite as simple as that. And you can go through various classes of event. And if you really care about X-ray binaries, this is where the classified X-ray binaries sit. Okay? But they will have X-ray detections as well. So you could bring in other wavelengths to help with the X-ray binaries. Young stellar objects tend to sit the other side. So this supports Elme and Thomas's work. And so your young stellar objects, be they flaring or dipping, will sit in this region of the diagram. But there's definitely overlap between these 2 classes, and we can have young stellar objects that sit below the sequence, which I find interesting. Our corona borealis objects, well, I'm a bit surprised because I thought they were all dwarfs, but some of them are giants, so that taught me something. And these are your microlensing, and I think we're going to understand that those parallaxes maybe need to be treated with a pinch of salt, but essentially, and they're also clearly getting reddened. But here are some of the classified microlenses in the same parameter space. So weirdly, some of our QSOs have parallaxes, or some things that we thought were QSOs are not QSOs. I don't know if Elme has thoughts in terms about that, but I suspect they are QSOs, and their parallaxes are not. They have non-negative parallaxes, and some of them are 2 sigma parallaxes, and that's quite interesting. And so this is everything that's unclassified. And so they actually straddle the same distribution of parameter space for these other classes. And so you can start to imagine doing a classification across multiple classes, not just young stars and CVs. I didn't talk about symbiotic stars. We'll hear about those later this week, later today, and other sorts of events. So I'd really like to work on exploring these data in a bit more detail. I'd really like to talk to people while I'm here about how to get the most out of this. I'm going to talk about proper motion as well in a minute, but we can also think about, I haven't used any parameterization of the light curve. I haven't used it. Did it used to be variable before an event? For example, could be a valuable indicator. Is there any periodicity? Could be a valuable indicator. And we publish the light curves for every single event published. So there's a lot of data in those light curves. They're incredible. And then, of course, for these, we also have, all of them will have ZTF data. Many of them will, if they're bright enough, will have test data. So there are a lot of other high cadence surveys that we could be exploring to combine with our Gaia detections. Or you could go the other way and look at the transients found in other surveys and see if they're also in Gaia. So they're doing repeat events in the different surveys. And what I haven't shown here is, well, what about WISE? Or what about GALEX? What about the ultraviolet? Or what's happening in the X-ray? So there's a huge kind of multi-wavelength analysis, I think, waiting to happen for our Gaia transients that I haven't seen done yet. It would be really interesting. In individual objects, case by case, people have shown me, oh, this event started in WISE before it started in Gaia. Well, what I haven't seen is a global analysis of WISE light curves or WISE variability compared to Gaia variability for large samples. And so I'd like to explore that, time permitting, and have conversations about that. Reduced proper motion I've defined as the apparent magnitude plus the proper motion, log of the proper motion minus some number. And I've demanded that proper motion error be less than 1.5 in both RA and deck. So this is good because it increases the volume of space to which you can include transients. So you get more of every class by not demanding it have a 2 sigma parallax. You can get more things, and you still get essentially an HR diagram. Proper motion gives you a proxy of parallax. Its nearest stars move faster than the away stars. So statistically, it still works. So we get more novae in here than we do in the parallax. We get more CV. We get more X-ray binaries as well, because a lot of them don't have parallaxes, but they do have astrometry, which can help classify them. We get more QSOs, because QSOs, so they're going to be a problem for all of this classification work. You're going to end up with QSOs polluting whatever you do. They're going to do that. And this was a really nice figure that we put in our paper. So the other thing we can do, and we can do from our spectra that we publish with our alerts, is we can extract the spectra, count the photons in the spectra, and plot the evolution in color of the different classes of events and show that the path they walk is also a useful classification metric. But again, we've not been doing anything with it, and I'd really like us to use that to find the things that people love: symbiotics, novae, X-ray binaries, the most unusual classes of event. So I'm going to finish a little bit early. That's good. Where we're going is, the first thing is that we've been trying to simultaneously observe Gaia transients with the Meerlicht experiment in South Africa. Sumeda can't be here this week. And so, but she's working on a paper to show what we're finding with this one field of view transit detector. So there we took a gamble and we say, okay, let's publish things that we only see once with Gaia instead of twice with Gaia. So you end up with a very much more noisy stream. And so Sumeda and Susanna in Leiden and Utrecht are looking at what those events are with a simultaneous observing strategy. So look out for the paper on that. Today, we've either already started it and I missed an email, or tomorrow, we will be running Gaia alerts in a fully automated mode. There are talks about this the last time everyone got together. So I'm not going to decide not to talk about the full automation today. But essentially what we've done is built a machine learning algorithm, set of them, based on human eyeballing over the past 7 years. And we've trained these machine learning algorithms. So we have random forest, we have PyTorch, and we combine those different machine learning algorithms to get as close to as what a human would say about an event as possible. And it's at the level of 99% as good. And we expect something like it would take you 5 runs of our system to get 1 false alert, and about 4 runs of our system to miss 1 alert that the humans would have found. But the humans are notoriously inaccurate, and so the machine may well be actually better. The humans can't agree between ourselves quite often. So that's what confuses the machine. So the paper is in preparation for that, and there will be an announcement coming soon to say we have switched it over to the robots. The robots are in charge. You probably notice, or maybe you won't tell the difference. I don't know. Maybe we've been doing it for a year and I didn't notice. And we need to do that because the humans need to do other things. They're not paid to do this. They've all been doing it out of the goodness of their time, their commitment to the project. It says a lot for the people who continue to do the eyeballing, continue to keep it going, because that exception, none of them apart from me was paid to do that. So that's phenomenal. We have to thank them. We will keep Gaia running until the end of the mission. The Gaia Science Alerts running until the end of the Gaia mission.
as long as our hardware doesn't fall over. And our hardware systems are due to run out of maintenance contracts at the end of May next year. So at that point, we're going to be in shared risk mode. And so we'll put warnings all over the website that this may stop. And we've already started warning people that there is a risk that we might have to stop. But we are exploring other hardware solutions for our system using supercomputers, a network of supercomputers in Cambridge that we have access to. It's non-trivial to move it. We need humans to help us move it across. I don't mean they don't need to carry computers. I mean they need to port the software to work on a different architecture. And I hope we can do that. I hope that's the solution. And I hope we can hire someone to do that, because we are hiring. So we have 2 job opportunities in Cambridge to work in the Gaia Plato area. And there's overlap between the personnel working in these projects, and there's Gaia Amsterdam. The Plato mission, which is exoplanet detection, will ramp up. And so we're hiring a scientist to work in that area, and we're hiring someone to work more in coding areas to work on both those missions. So I leave that there as links to the jobs all coming to you. And I'll finish there and take any questions. Thank you.
Thank you very much. Okay, so lecture room. Any questions, please? Lukasz, wait. Anybody else? Pavel.
Hello, Simon. Thanks for the nice talk. 2 questions, 2 issues. First of all, I would like to ask you about your color magnitude plots and parallaxes from Gaia DR3. Did you compare them with Baylor-Jones' work?
No. So what I was showing you today was me playing with the database in a very fast way to make some pictures to show what you can do if you explore the data. The correct way to do it is to use something like the Baylor-Jones Bayesian extraction of distances and look at your priors and do it all in a clever way. But this was just, can we see differences between different populations if we explore parallax? The answer is yes. So no, I haven't done the thorough one. That's what I'm here to do and talk about, is to do it properly.
You have chosen the best parallaxes with the lowest uncertainties, right?
No, I took all parallaxes up to sigma for all alerts, and then looked at the ones who were classified and those that were not.
Okay, I see.
So it's just a data mining, let the data speak, what do we see?
Okay, thanks. And the second question is, what do the sizes of the points on these CMDs?
Yeah, sorry for skipping over that. This is the amplitude of the alert, and it scales as some number times 2.5 to the delta magnitude. And I can't remember the scaling. I just made it up until it looked exciting.
It is.
I wanted some big ones. Yeah.
Okay, any more? Okay, Lukasz, now you can.
It's a question from Zoom. Jakob is asking, thanks for a nice talk. Did you explore going deeper than 90th magnitude for new transients, especially with the new ML tools?
That's really interesting. So the single field of view detector, we are pushing fainter, not to 20.7, but down to, it's in Susanna's paper, I can't remember the number, 20 point something. And those are not public yet. We had them all public for 2 months while we were running simultaneous. They will be public at some time when we publish the paper on the rates of contamination. So there are 2 factors. One is we are pushing deeper by over a magnitude, and the other is that we only need to see an event once, and we do a lot of more aggressive filtering. So we avoid the plane, for example. We avoid the ecliptic, for example, those. But the hope is that if we can overlap with, for example, the gravitational wave experiments, then chances of Gaia seeing something would give a really, really nice detection, even though our daily area is only 1,000 square meters. discoveries a day. It's not huge.
Okay, any more questions?
That's one.
Okay, Lukasz again.
This is a question from me. So the parallaxes for novae, like here, you only get them in very, very rare cases when you see the nova in quiescence. But we've seen many novae without the component, right? And the same applies to CDs. So there is probably a different population of novae and CDs for which you don't get parallaxes.
No, absolutely. And that's why I drew the distinction between parallax and proper motion. Because if you go to reduce proper motion, you increase the volume and you increase the sample of novae. And then you're right, there are another set which we never see in quiescence. So you don't get parallaxes for, you don't get proper motions for. So those again, and then you have to you classify it now or you never see it again.
Well, it's interesting actually because they will eventually get some Gaia proper motions, I guess, because there will be measurements in DR4, for example. So if the nova was lasting long enough, that's actually a question, higher to astrometry people in Gaia. If they see something which was not there for many, many years and appeared for a couple of months, whether they are able to measure a proper motion, maybe that's not enough, not long enough.
I would guess not long enough. If you look at Adam Kawasz's paper, which is from earlier this year, he looks at the completeness of novae discovery with Gaia versus assassin and computes the observationally measured rates of galactic novae and compares them to predicted rates and compares them to extragalactic rates from 31. So that's, and he was here last year talking about it. Now his paper's all accepted. So it's cool. Thanks.
Okay. Any new questions? Nobody? Lukasz, Zoom?
Yeah. There is a question from Josh. Is there somewhere a list of interesting alerts to follow up outside black hole TOM?
Which Josh? Is that?
Just one.
It's for a beer.
Hi, Josh. So we've always, Lukasz has always been our curator of this is the most exciting thing, go and look at it, please. And we need someone to do that work because we have a big stream. Some of them are, most of them are quite faint. And so unless you have someone cherry picking the really exciting things like Lukasz has been doing, they can get overlooked. So if I would appeal to people to join Lukasz on this crusade to promote the most exciting things and put them into the black hole TOM.
Yeah.
And but only if Josh can read the black hole TOM. Otherwise, we need a website as well. Yeah, he can. So yeah, just more help, more eagle eyes, and promote more transients would be my suggestion. I don't know if that helps, Josh.
I have one small comment because I remember my first job with Lukasz and with Gaia, and I was looking for transients, and it was, oh my god, but it was, I don't know, 8 years ago, 7 years ago, a lot of time ago, and it was really hard work. So now I'm really happy about machine learning and so on. So really good that you made that. Okay, thank you. So now coffee break, please. We have half an hour. So 11:30, we're meeting again here. Take a lot of coffee to have more questions. And thank you.
And the coffee break is served in the bar because the weather is nice, so we have to walk all the way to the bar. So make sure to take into account the couple of minutes you need to come back here roughly on time.
This room will be closed. Yeah, but we can leave the laptops here.
We can leave everything here, for this half an hour. And actually, there is a Nobel Prize announcement coming up in physics in a minute, and we're going to watch it in the bar. Okay.
Although the announcement itself will probably
Yeah.
ceremony is not.
Thank you.
Czy my wyłączamy, czy nie?
I think.
Yeah, because that's right problem is
Monia, znajdźcie technika, powiedzieć może trzeba naładować.
Pewnie.
That's, yeah, the thing I mentioned that Gaia is covered many candidates before. That's the problem. It is just very there. But if you, for example, combine this with the infrared observations, but that's the way how I see it.
What you've done.
Yes, it's for cities that you could say they are able to look in the light.
Yes. Thank you very much.
Yes, yes, always time long.
Yeah, the guy the bigger first one. There is another I think that now we have first I will present today. We have the first today. And the only thing we are waiting for is the first preparation. But that would be problematic because their outbursts are very slow. Actually, there was one no was the outburst. But basically, from all the outbursts, there's one message.
Where's your actual flight?
I'm 31.
Very excited. I'm going to turn that off.
We will fight more because smaller. Actually, there are not many. Right. Look for them. Convert. That's one.
No, tak mówisz, ale ja... Są po prostu
Gdzie tam? Tam jest tam to kurzowe, to się nie przyklei do tego kurzowe. No dobrze. Przypomnijmy, zobaczymy, czy będą odczytane. Za ładne Egy 2 percig tudni szólhatok?
Igen.
Kornel, mam dla ciebie zadanie. Kupiłem mojego iPada. Patrz.
A Maja go przyniosła.
O, kochana Maja.
Ja oddaję iPada.
Dzięki, Maju. Laszlo?
Yes, I am here. Can you hear
Hi.
me?
Yes, we can hear you. Can you start sharing your slides?
Okay. I will share the screen.
A, tu leży.
Okay. When it comes to as long as that's not.
Yeah, no.
We don't see your slides.
Don't you see?
No.
It's a problem.
See your slide. Czekaj.
Okay, we have small technical issues as always with Zoom, but please take your seats.
Yeah. No, do you see?
No. You're not
Oh
sharing.
my God.
If anybody needs water during the lectures, you can take it from here. So enjoy.
Lukasz has my presentation. If you can show.
Sure, but we can spare a couple of minutes because it worked. We checked earlier,
Yes,
right?
yes,
So
but
just start sharing your screen again. And because now you're not sharing your screen. I think that's the main problem.
Don't be shy.
All right, Laszlo, I'm going to start the
Yes, thank you.
Send me. Okay, so just you need to tell me next slide and I will be switching.
Yes, yes, thank you, thank you. I don't know why this refused to work. Morning, it worked well. Yes, thank you very much. So, first of all, I thank you for this opportunity to speak about Gaia third data release. It's a huge result to have the access to this tremendous amount of data. So it's impossible to show all important results. So I will mention very briefly some selected results. The next one, please. Next slide, please. So I recall that this is the third data release, and every second year there was a data release with ever growing amount of scientific data. And now the third data release contains data about 34 months of observing time, which is less than 3 years. So we are the data collection is much ahead of this data published. The next slide, please. I will mention about the variable sources. Nevertheless, there are many other data, radial velocities, time series, spectra, astrophysical parameters, which are very important, chemical abundances of about 12 elements. The next one, please. And the DR3 expands the early DR3 with publishing much more astrophysical informations, and not only stars, but the extragalactic sources, quasars, galaxy candidates, solar system objects, much more than the previous ones, and extinction maps. Next one, please. Here is the variability. I recall that in the general catalog of variable stars, there are only 52,000 entries, and now the Gaia DR3 contains more than 10.5 million sources, variable sources, which is a tremendous increase. And the space photometry was detecting milli to micro magnitude variations. So this is why in the title of my talk there is a micro variability, and the megavariability means these extremely large numbers of variable sources. This is the brightness distribution of the 10.5 million sources. It is seen that in most cases they are in the brighter domain of the sources, and the probability to reveal the variability is higher for those cases when there are more observational data. So that means that in the coming years this number will increase more and more. The next slide, please. Here I list those papers which have been published together with the Gaia DR3 data release. They will form a special issue of the journal Astronomy and Astrophysics, and they will appear within several days or weeks, but all of them are available in the AstroPH. This is the flowchart of the analysis, which shows the very complicated and very thorough analysis before publishing them in a scientific paper. The next one, please. This diagram shows that most of the newly discovered variable stars are pulsating stars, and the second are the rotational variables, and many eclipsing systems are in the data sample of variable objects. Here are some numbers showing the greatness of this data release. The next one, please. And the boldface means the most numerous class of the objects published in the as variable sources. There are altogether 24 types of variability listed here, but not only variable stars, but there is a group of active galactic nuclei in this sample. So Gaia Coordination Unit 7 deals with all variability phenomena observed by the Gaia. The next slide, please. Here are again some numbers showing the exact number of the individual variability classes published in the special papers, including the active galactic nuclei, compact companions, the solar-like rotation modulations, RR-like variables separated into several subtypes, and the low amplitude delta Scuti and delta gamma Dorado stars. The next slide, please. Here is a famous figure showing that the Hertzsprung-Russell diagram is full of pulsating variable stars. In this diagram prepared by Jeffrey and Sayo, only the pulsating variable stars are reported. On the right side, the Gaia DR3 data for the LMC and the SMC Small Magellanic Cloud, and these diagrams contain all types of variability, not only pulsating. There are eclipsing binaries and Coronary Borealis stars and others. So it is obvious that every part of the color magnitude diagram or Hertzsprung-Russell diagram is filled with variable stars. The next one, please. Some light curves. This is a microlensing event, emission B star, an active galactic nucleus, an Coronary Borealis star, sudden dimming, a supernova, a rising part of the supernova light curve, and this is a long period variable star, which will be mentioned later on in this talk, but the others will not be mentioned in detail. The next slide, please. Let's start with the youngest variables, young stellar objects. Here, the selection criteria were the color, the brightness, the distance, and the celestial position. And in their paper, Gabor Marton and his co-workers compared the distribution of the Gaia sample, which is based on an unbiased all-sky survey, with the previously existing Konkoly catalog of young stellar objects. And it is seen that many new young stellar objects have been discovered, mainly near the galactic plane, but there are some at high galactic latitudes. The next slide, please. The rotation modulation, these are mainly solar-like variable stars, but you see that some light curves show long-term coherence and other light curves, so the absence of long-term coherence, which refers to the migration of large stellar spots and other phenomena. And here is the distribution of the rotational periods from several hours to 5-10 days. It's a very interesting diagram for solar-like stars. The next slide, please. Ellipsoidal variables with compact companions. There are 6,300 such stellar pairs in the DR3, and they are found mostly near the galactic main plane. And here again, those systems could be studied better, which have been observed more than 25 times. The companions are possibly neutron stars or black holes. This means that each of them is a very important and interesting system. The next slide, please. Here again, some light curves of such stars and the color magnitude diagram. The next one, please. Microlensing events, which have been discussed by, will be discussed by Lukasz and Katarzyna. Here I show only the distribution of the observed events and mention that in DR3 there are 363 such events during the 34 months of observations. And the next slide shows the end of their table published in the DR3 papers. So this here you can see that the last one is has a number, serial number 363. The next one, please. There is a very interesting paper or study, the Gaia Andromeda Photometric Survey. There is a circle with a radius of 5.5 degrees around the Andromeda Nebula, and this part was studied separately, and there are more than 12,000 variable stars in this Gaia Andromeda Photometric Survey field. These variable stars can be studied separately and already shows the importance of the extragalactic variable stars. The next one, please. Here are the color magnitude diagram of the Gaia Andromeda Photometric Survey, and these particular areas are mentioned here separately. I am sure that this presentation will appear on the web page of this workshop, so you can read and get more information about this slide too. The next slide, please. Variable active galactic nuclei. There are two samples, the Gaia variable AGN, about 872,000 objects, and the candidates to explore. And this distribution of these both samples are shown in this diagram. And here at the top you can see a typical light curve brightness variation of an active galactic nucleus. The next slide, please. Here are some light curves, a BL assertive type, in the middle Seifert-1 type, and the radio quiet quasar. The next one, please. Long period variable candidates, again, the distribution and the period distribution as compared with the Gaia DR3. You can see that now there are more and more shorter period, long period variables. And here are the long period variables in the Andromeda Nebula. The next slide, please. The number of known long period variables has been increased by a factor of 6 with respect to literature data. The next slide, please. Here are the period luminosity relationships for long period variables with different branches showing the different pulsation modes or binarity. And even in the local group galaxies, there are very many long period variables discovered. In the LMC, more than 40,000. The next slide, please. Mean sequence pulsators. Here, a very interesting result is that the empirical instability strip is broader than predicted by the theoretical lines. Here you can see the theoretical lines and the observed ones. These are mostly very low amplitude variable stars of type slowly pulsating base stars, B stars, Gamma Doradus, Beta Cephei, and Delta Scuti. Next slide, please. And very interesting result that stellar rotation attenuates the amplitude of the dominant oscillation mode of Delta Scuti stars. Here are the amplitude and here is the amplitude distribution, and in this diagram the photometric amplitude as a function of the V sin I, the rotation velocity. It's a very interesting new result. The next slide, please. Here the period luminosity relationship of Delta Scuti stars and its continuation to the Cepheid period luminosity relationships. So it's likely small brothers of Cepheids, the Delta Scuti stars. The extension is almost linear. The next slide, please. No, the RR Rayleigh and Cepheid stars would follow, but my time is very short, so I will only flash these slides. More than 27,000 Rayleigh variables have been discovered in the Gaia DR3 data. And typically 40 observations are available for each star. The next slide, please. Here are the light curves. Left are the galactic stars, and in the right some extragalactic Rayleigh variables in dwarf galaxies, Sculptor, Phoenix, and Tucana 2. The next slide, please. Here are the period amplitude relationships and as a function, the colors means the metallicity. The blue are the metal deficient and the red are metal rich stars, and you can see the progression in all diagrams. The next slide, please. Even radial velocities were published for some error stars and bright Cepheids. Here are the magnitude distribution of this sample, and here are some example phase curves of brightness variation and radial velocity, which can be studied separately. Next slide, please. Here are the distribution of the Cepheids in various galactic systems. All sky means the or Milky Way and the dwarf galaxies nearby. Next slide, please. Here again, the sample light and radial velocity curves of various subtypes of Cepheids, double mode, first overtone, fundamental mode pulsator, and so on. The next slide, please. Here is the Cepheid celestial distribution in the Magellanic Cloud, in the All Sky, and M31, M33. So many extragalactic Cepheids have been discovered. Next slide, please. Here are the Fourier parameters distribution, which characterize the shape of the light curves for the All Sky left and for the anomalous Cepheids, for the classical Cepheids top, anomalous Cepheids in the middle, and type 2 Cepheids, BL Hercules, W Virginis, and RV Tauri stars in the lower panel. The next slide, please. Here the period luminosity relationships, which should deserve a longer discussion, which is impossible now. Let's move to the next slide. Here are the amplitude distributions as a function of periods for various Cepheid subtypes, and these are for the astroseismology, the Peterson diagram for multimode pulsators, which again cannot be discussed in more detail. The next slide, please. Here the metallicity, which can be determined from the light curve shape only, and here is the comparison of photometric metallicity values to the spectroscopically determined metallicity. From the literature, you see that the photometric metallicity is a good estimation. Not perfect, but this can be instructive. The next one, please. And here you can see the progress from the Hipparcos period luminosity relationship of Cepheids and RLI stars, and moving up and up. This is Gaia DR1, DR2, and DR3. And for the RLI2, so which indicates that with the forthcoming Gaia data releases, we will have a very good period luminosity relationships, which means that the calibration is almost perfect, and the cosmic distance scale will be based on a very good basis. The next one, please. And this 10.5 million variable stars isn't the final number. I recall to the Hipparcos color magnitude diagram, which shows the distribution of variability on the Hertzsprung-Russell diagram. Red color means that all stars here are variable, and blue means a decreasing factor of variability. So in the Hipparcos sample, there were about 10% of variable stars among the 118,000 target stars, but Gaia investigates more than 1.8 billion stars. So I expect that at least 100 million variable stars will be revealed in the forthcoming Gaia data releases and the final catalog. The next one, please. Towards Gaia data release 4. Here I copied the latest announcement of the Gaia DPEC, which means that in next year there will be a focused product release which will contain 6 different flavors of data, and you can read this in the conference webpage. And the last slide, Gaia DR3 will include all time series data, epoch astrometry, broadband photometry, radial velocities, and spectra for all sources. And there will be a DR4 within several years. This will be the final data release from Gaia mission. And we are looking forward to use the Gaia Legacy Archive too. Thank you for your attention, and apologize for this technical problem. Thanks.
Thank you very much. And because of the technical issues, we don't have time for questions. So if anybody wants some question, please do it on Zoom, by the chat, or on Slack. And right now we will go to the next presentation. It will be a really short one because it's poster presentation, and it will be William from Paris Observatory. You have 7 minutes for your presentation. Lukasz, are we ready?
Yes, do you hear me?
Yes.
Okay, and you see my screen, I hope.
Not in the presentation mode.
Not the, please switch to the presentation mode, because
Oh yes, try it. This one. It's okay?
Yes, please start.
Okay, well, I present a work related to the Gaia alerts, in particular for the solar system objects, and also the beginning of professional amateur activity. And here you have all the people directly involved in this work. Well, the Gaia detects new solar system objects, and we have organized a network, the Gaia Fun Network, SSO, in order to make the follow-up of this detection. We have the difficulty to have good ephemerides due to the short arcs detected by Gaia, and we use a statistical method to provide the sky map in order to retrieve the object from the ground. Well, and the goal are to improve to validate the detection and to improve the orbit through the Minor Planet Center database. Well, we need observations from the ground. As you can see here, we had already more than 300 MPC designation for 400 detections since the beginning of the year. And you see on the graph that we have many more Gaia alerts than the ground-based observation. So we need observation from the ground, in particular with the amateurs, because the mean magnitude of this detection by Gaia is 20.3, and amateurs can detect the brightest object. And also ground-based astrometry for detection and validation does not require a high signal noise ratio. Well, one of the results is that we saw that we have a strong bias in inclination and eccentricity for the detected object. And the question is it an observational bias, which is strongly possible, or other? And this kind of work has been described in a recent paper by Gerry and Al in 21. You have the address there. Well, the work with amateur can be organized thanks to this kind of new network that we initiated this year. The name is RAPAS. It's a name for French Réseau Amateur Professionnel pour les Alertes Scientifiques. We encourage amateurs with their camera, CCD camera, CMOS camera, to observe in astrometry, photometry, or even in spectroscopy. This activity is supported by the Scientific Council of Paris Observatory. We have financing for the manufacture of specific filters, and we also for the organization of workshops. And it can be for 3 years at least of support by the Paris Observatory. And we have a kickoff meeting next weekend, to be held in Paris Observatory. Here's the agenda, and I don't go in detail, but you see all the participants, which are as well professional and amateur, in 4 sessions. The first session on alerts, a second one on filter specification design, the third in photometric reduction, and fourth for next activity, and it will be more for spectroscopic follow-up. Well, the idea was to encourage amateurs to use filters compliant with the Gaia band. And for this goal, we make the new filters in order to provide them to small, at first, a small number of amateurs, 25 amateurs. And we see that it will be very useful to get this harmonization of photometric observations. We had a call for participation to the alert observations in June by the French Société Astronomique de France, the main amateur society, and we already have 18 amateurs registered for these observations. We also have the collection of the important telescope characteristics, and you see on the graph that we have several telescopes with a diameter greater than 50 centimeters up to 80. And we think that it could be very useful for this goal. And here you have the summary, and this is the last slide. Thank you.
Thank you very much. Any short questions for now? Zoom? Any questions, Lukasz? Zoom?
No, I don't see any. I might have one. Hi, William, this is Lukasz here. This is very great. I was actually very much impressed by your idea of the Gaia GVP and RP filters. This is something what we will definitely appreciate
also for our network. So I'm happy to talk more about this because of all the calibrations issues. We've been calibrating different filters to Gaia. Why should we bother if there are filters available, which are specifically built as the Gaia filter? So that's very impressive work. And I'll see you on Saturday.
Yes, thank you.
Okay, so thank you very much, William, again. No more questions as far as I see. Okay, so thank you very much. And the next lecture is Lukasz Wyrzykowski.
Wait. Right. Okay. Hello again. It's me again. This is my. Sorry. Move it. See if I'm technically working on my own slides. Okay. Right. So here we are. I mentioned we've been having these workshops since 2010, and here we are here. And there are more to come, of course. But I just wanted to flash this slide here just to make sure that you are aware that all the slides and archives and videos are which we record now, and they've been recorded also at previous meetings. So go to that page here. I'm using my laser pointer. Good idea. So there is a link there. You go there, you can find all the recordings from previous workshops and things like, boring stuff about Gaia, what Gaia is, for example. We don't need to repeat that because we actually displayed the video from last year. Gaia is there, nothing has changed since then. And you see a nice gallery of nice posters produced by various people. So anyway, so my talk is just a brief introduction why we are here. So it's going to be a recollection of some of the ideas which brought us here. So I call it a follow-up network for time domain astronomy. That's what we are doing here, right? We are a part of the ORP network, ORP grant, the Opticon RadioNet pilot. We've been part of previous Opticons twice already, two generations of Opticon, and we hope we will keep doing it. But I hope Gerry will still support us if we provide him some feedback, right? Okay, a couple of faces. Most of the people from that group are here, and also I flashed some sponsors. We are supported by ORP, but also we're using some Polish money as well to support our activities. And we also have a web page. We've just built our web page recently, so go have a look. Gaia Astro. Yeah. Right. So time domain. Is this one better? 1, 2, 3. Okay. So time domain. Mostly people think transients, and I think this is very wrong. This is what I'm trying to fight. Time domain is all what changes on the sky on timescales, and we're talking about timescales of milliseconds to years to decades. And now I think astronomy has reached this era that we have this data available. We're collecting more and more of this data, and I would say we're even overwhelmed by the richness of the data, and I think we're underexploring it. There is so much data that we only focus on some aspects of it. Someone builds a survey and then goes using only the data from its own survey, or someone is interested only in supernovae, then they only go after supernovae. But there's way more of things to explore, and I think our creativity and imagination is our own limitations here. So I show this plot here to show that, as an example of Gaia Alerts, it's just one of the time domain surveys. And as you could see in Laszlo's talk, actually,
time domain is not only transient, but there's all those variable stars. This is also time domain, right? And there's a huge wealth. And also with Gaia, we can observe the whole sky, right? So we have targets which are time domain suitable all over the place. They're everywhere on the sky. So wherever your telescope is, wherever you're located, there's always an interesting target above your head somewhere. And also at any moment of time, there is always an interesting target which has to be observed. And some of those targets, they require rapid reaction. Some of them require less rapid reaction. Some of them can be observed really in a relaxed mode whenever there is weather, for example, but it doesn't influence the science case because that's not important. Of course, it depends, it varies from science case to science case, but in general, that's the whole idea. And there's of course many other surveys. Simon has mentioned some of them, but we're very greedy. The astronomers are greedy, and we're building more and more surveys and telescopes. With Vera Rubin being an example, there Vera Rubin will cover most of the sky, well, mostly in the south, but it will move us few magnitudes deeper. That's going to be a huge challenge. So we should learn very quickly from Gaia and from other surveys which are gentle on us and they don't go that pain. But with LSST and Vera Rubin, we will be in trouble if we don't learn our lesson now. Couple of examples. I like to show this one. As you know, my favorite science case is microlensing, so I'm biased. Not hiding this. So we first thought this is a very nice microlensing event, very long, bright, and worth following. So we got our network, observe it for many days. You see the time scale here of observations about 1,000 days. It's impossible to get 1,000 days of observations of a target with a single telescope or with a single proposal. So you need a network like this. And so we've been observing this one, and it turned out that it's some kind of FU organic star. Boring for me, but very interesting for others. So there was a paper published by our Hungarian collaborators where we combined the follow-up network data, optical data, infrared data from WISE, which we actually got for free, which was there. So there is many surveys and data lying over in different places, which just has to be connected. So that's an important point. So this was one of the nice examples. And of course, a microlensing case, and this was the Gaia 19 BLD, probably one of the brightest microlensing events ever detected. And we've covered it very intensively, with thousands of observations. The timescale here was much shorter. It lasted like about a year, maybe less than this. But we've used multiple facilities all around the world, including not only photometry, but also spectroscopy, including interferometry. We use VLTI for this, and we essentially solved this one. We found a dark lens with a mass of 1 solar mass. And there were actually 3 papers published out of that one very event. So that was actually very interesting. So the network. This is a map, which is probably not up to date. And Pavel is always correcting me that you, again, used the wrong map. There is an updated map somewhere, but it doesn't matter that much at this very point. If your telescope is not on this map, apologies. But the idea you can get from that plot. We need telescopes everywhere, right? As I said, there is an interesting target anywhere on the sky or in any moment of time. So you need to be covered both from both hemispheres and also south, north, and also east, west, right? Any time of the night, of the day is when we need telescopes. Also, the weather patterns, they are very different. So the more telescopes you have, then the more safe you are in terms of availability of a telescope at a given moment of time. Hence the network. And the network was actually initiated before Gaia was launched. When we were working with Simon and others in Cambridge, we realized that there's going to be these very interesting alerts from all over the sky, but who's going to observe them, right? So the science would be wasted if they were not being observed. So we started collecting telescopes and inviting them to join the network. And at this moment, we have about 100 telescopes
which are cooperating actively with us. Some of them were active in the past, some of them joined recently. Generally, the idea is that we invite people to join this scientific endeavor, mostly on voluntary basis. And so, as Gerry was saying, this is a very interesting funding model, because people donating their own time, they don't get money out of it, right? The only money involved in that schema is that I'm not even paid for that at all. I just have my lousy professor salary at the University of Warsaw, and that should cover all my activities. And there are some people who are directly paid from the ORP grant, and these people are actually maintaining the infrastructure we run. They coordinate the activities, and they process the data, they react, they support users, and so on. So this is where the money is needed, and this is the only place where money is needed. Other than that, the telescopes, they can get our support. We can help them if they donate time voluntarily. We also apply for time because very often this time telescopes are available through proposals, and I have a list. These are nice pictures. First coming. Some of the telescopes you might recognize, some of them. But anyway, we are also applying for time through regular proposals, and that's actually quite an impressive list we compiled yesterday. That we look around where the telescopes are available, and of course there is Opticon. We keep applying for Opticon. Sometimes we don't even get time, but whenever there is Opticon time available, we apply for it. So we actually get time on some of the telescopes within Opticon transnational access. But we also apply for Chilean time. There is a lot of telescopes available for Chilean time, and they would be sitting there doing nothing if it wasn't our proposal. Sometimes there are cases like this. Of course, it doesn't count LCO, for example, which is extremely busy and oversubscribed. But some of the other telescopes, like Prompt, T80, SMARTS, and so on, I think if it wasn't our applications, they would be sitting there and they would not be used at all. So that's a long list. We also go for spectroscopy, interferometry, and so on. But this is sometimes it's tuned to our microlensing science case, of course. And we collaborate with other people as well who have some spectroscopy time, for example, and we follow different types of alerts as well. So this is my plot I've been showing many times, you've seen, but I'd like to go through it again. That the philosophy here is that we have surveys surveying the sky from the ground, in radio, from space, and they produce alerts, right? These alerts are then filtered for brokers. And these brokers, this is where users interact with the alert streams. And so if someone is interested in supernova, right? The user says, okay, I found this supernova in M81, I'd like to have this observed. Or someone is interested in microlensing events, and there's this guy at 20 FNR, for example, and they want this event to be observed for 1 year. So these are the requests people can, users, the scientists, they can produce. So we react to, so the system we built reacts to those requests. And these observing requests, they are then sent to our black hole TOM system, BHTOM .space that we address. You'll hear more about this through the entire workshop. Here, this is what we are trying to advertise. And Przemysław will cover more, and there is going to be a workshop tomorrow, hands-on session tomorrow morning for those people who want to improve their skills on using BHTOM or learn more about this. This is not, if you don't need that, you don't have to, but tomorrow at 9 a.m. we're going to have the hands-on session on that system. Anyway, so that system is taking care of the requests. So for example, there is this request for microlensing event to be observed, and the system is handling the cooperation, the discussion with the network of telescopes. And here, of course, it depends. If the telescope is manually operated, there's a person sitting there and looking, okay, what is now interesting to be observed, then they put it in their schedule manually and they observe it. If the telescope is a robot, then the request can be handled automatically, and the request can go into the scheduler, and the telescope can observe it whenever suitable. So we are flexible. We can work from robots to humans. Also, we have a large number of amateur astronomers involved in that, and they are just they have beautiful instruments sometimes, and they just need to know where to look, where the science is. And moreover, so that's not only it. So here, that's probably easy to reach that stage, to have someone observe your target. But the problem starts when there is data, right? People take thousands of images and then what? And normally it was done the way that the astronomers, the scientists, they were swamped with those feeds files. They sometimes had no idea what to do with it, or they have done this, 20 years ago, and now they have their drives full with feeds. And then what? So our system is actually taking care of that bottleneck and is processing the data received from the telescope. So these scientists, they don't even get to see the actual feeds files. And moreover, the system is asking all the archives around, like WISE, we're planning to expand it to other wavelengths as well, and radio as well. So the scientists, they will also get any auxiliary data, serendipitously observed data, whatever is there on their target, right? Sometimes they can find it themselves, but our system is going to do it for them. And what the users get in the end is the science-ready data products. And what I mean science-ready data products, mostly light curves in multiple filters. And these light curves are kind of dynamic. So the more data is being collected, the light curves are growing. But also we are working on time domain spectroscopy, and there's a placeholder for that. We're working on expanding on this as well. Yeah, and then in the end, there are publications coming out, right? These publications are to be written by the users, the scientists, and all the people involved in that process are typically invited to co-author these papers. So this is the actual, some screenshots of the black hole TOM system. I'm not going to spend more time on it, but I will just emphasize that this is built on open source, beautiful code called TOM Toolkit, Target Observational Manager, prepared by Laszlo Szabados Observatory people. They were pioneers in that kind of business. So they provided the open source code, which we use as a platform for our black hole TOM. That's why we call it black hole TOM. Black hole, you know why. Okay, these are some of the publications we produced so far, and there's even a tab in black hole TOM which helps producing tables. If you just click publication, download the table, it produces a tag ready. You just copy paste it in your paper, and then you have a table with all the data, all the observers, all the filters collected. So in summary, so there are opportunities for scientists. So this is a virtual tool for long-term monitoring, 24-hour coverage. It's a global telescope, and we can observe your target anytime, right? For telescopes, if you have a telescope and you want this to do something useful, we will tell you which target is of interest for observing. We will process your data, and we can even operate your robotic telescope. So the plans, there's a lot of plans what we can do with that tool. So I just listed a couple of my dreams here. So automated observational requests, this is still to be done. Spectroscopic data processing, it's almost done. Automated processing of collected data. So for example, the REM archive is queryable. So we will create a direct connection from black hole TOM to the REM archive. So whenever you observe our target through REM, the data will automatically be processed and will be there on the light curve. Of course, we want to expand our network. So if you're sitting here or you're listening to us and you have a telescope which is ready to or would be interested in joining us, then let me know. We were working on connecting radio telescopes, and this is in progress, mostly with Toruń and Sardinia as well. And we have some ideas of some pilot radio and optical time domain observations, mostly like something like quasar monitoring of transients. If you have any other ideas, please let me know. And talk to us if your telescope is robotic and we can accept observing requests from your scheduler. This is something what we plan to expand more, so that the roboticness of telescopes is actually being used by our system. And I think that's all I have to say. Thank you.
Okay, so any questions?
I'll be around.
Lukasz is around all the time. Please.
Lukasz, you said that there is some kind of interface to the robotic telescopes. I was wondering what kind of software handles that?
Well, the software problem is on the telescope side, right? We can talk to a telescope through our requests. We don't have any special software for that. We just build there's a special protocol for that. That's for sure. It's called EON. It was also designed by
that's EON.
That's EON. But we can actually talk about any. ABOT also can be coded in. It doesn't matter. We're not limited by this. And we can accept whatever your telescope is accepting. We can code it in.
And I have a second question.
First one.
Okay. About this alert system from BHTOM. I've been using BHTOM since spring. How to get the list of addressee of these alerts?
How to get to
the list of the addressee of the alerts?
You want to get the list?
Yeah. I want to get the alert. So, do you want me to put to the list of?
You have your own target, you mean? Yeah. Okay, you just add it there. Every user can add a target to BHTOM.
What about the interesting targets you have, and you propose to observe one other?
Well, so the way it is organized, but we'll talk about it more in detail later. So they're sorted by priorities, and these priorities are assigned how interesting the target is. So essentially, you just sort it by
the priorities that the observer.
Yeah.
What to do?
Yeah, exactly. Well, we'll talk about. I think Przemek will talk about it more, and tomorrow we'll also cover it. But that's a very important point: how to select effectively, how to select targets for interest, because you cannot observe 200 of them, right? You want to select a couple of them, and which ones to choose. That's a very good point, and that sometimes we don't realize that there is a need for this. Okay.
Hi, this is Josh.
Yes, exactly.
Yeah, I put the question into the chat. I mean, you mentioned the automated observation request. I mean, how is this done? How do you distribute this to users like me? I mean,
well, yeah. So it depends on your actual setup. So if you accept an email, we can send you an email. If you have a fancy scheduler, we can talk to your scheduler. But we're just flexible. We tune to the actual telescope.
I prefer an email.
Sure. Yeah, we can do email. Yeah.
Okay. So thank you very much. We have. I got the microphone. We are out of time. So Przemek, please. I hope you will be fast.
5 minutes.
It's something about.
So.
Okay.
I don't think so. So the next person probably will be forced to finish early.
No, don't worry. We can run over a little bit.
Yeah, we have 90 minutes for dinner. So.
Okay. Yes, sure.
Okay. So hello everybody. I will try to be quick and skip over some of the slides that Lukasz already partially covered. So you already know what BHTOM is. It's easy to use open access service for providing science-ready photometry. It's based on the open TOM toolkit. It
allows everybody to manage their own observations or to science teams to gather observations from everybody. It's very easy to process your own files. You don't have to be a scientist to be able to get science-ready light curves. It's as easy for amateur astronomer as it is for professional one. And the fifth star here in the slide, which already Staszek covered and Josh in some case, it has the capability to trigger observation from remote observatories, which is the point that we are probably want to get to minimize the work hours of our team. And this is the same case as Simon mentioned before. We want to use people for much more complex stuff. And tomorrow in the morning and at 9 there will be a hands-on session, which in which me, Paweł Zieliński, and Maja Jablonska will cover all the things that are to deal with BHTOM, uploading files, working with your data, browsing for light curves, and so on. How it works already was already covered by Lukasz. So BHTOM is the tool that manages everything. When you are an observer, the only thing that you care about is to upload your files either through web service or through Python script. For now, we don't have any other option to upload your files. I know that, for example, Josh does not use Python and he would like to be able to use some compiled program, but we will maybe try to figure that out in the future. So I will not elaborate more on the engine, which is CCDPhot, and that covers the photometric processing. It's basically a pipeline built around open access tools. We didn't want to use anything that have to be paid for. So what happens? We have two sources of data. One is basically an image of the sky, and the second one is the dictionary that contains all information about your observing site, as well about your instrument, your telescope, filter system, and so on and so on. And what we would like to have, we would like to have photometry for each source in the frame, the image frame. Of course, for now we are using only the single measurement for the event target that we are interested in, and some other measurements to standardize the photometry. But all in all, we can use photometry for all the stars. So BHTOM is becoming like a huge database for light curves, which we will produce, I guess, in the future for you to have a look at. So in the field of, for example, Ayers Rock, which some of you probably observed, there will be hundreds of variables, maybe some transients, some planetary transits. So this is also a byproduct of our work. And the main thing that we use here is the automatic selection of stars for PSF fitting, which provides a very coherent, homogeneous results with very low loss. Here I have an animation of how it works. I will skip on. You can see here that the processing of a single file takes 30 seconds. In case of this particular field of view, we use this raw calibrated data. For now, we don't have an option to calibrate the data for you. You have to use the bias, the flag, and so on. And maybe in the future we will. And we use side telescopes and instrument info. And the result is a fits header that is updated with your information. The WCS astrometry with Gaia DR3 already. We switched to DR3 a couple of months ago. And 3 types of photometry, 2 apertures and 1 profile. And in each particular case, we are trying to guess, to extract which one is the best for this particular frame. And that one is used to is uploaded to BHTOM to be displayed in the light curve. here are some examples of how our pipeline cleans the images from stars. Here is a sparse field of view, a little bit denser, but with nebula present. You cannot see actually here in the eye filter, but it's there. Here, yes. And a very dense field of view. It's also cleaning the, producing the residual image very well. So now about the evolution of our telescope size. In January 2021, we basically started. We had a year when we tried to set up the gear, and in January 2021 we launched the service, and we had 26 instruments in our database. Last year in Crete, we added 14 to the list, and I promised you that by this workshop we'll be at 100. Unfortunately, we didn't make it, but 75 and 2 in testing is pretty good. We have the list of some other telescopes which are interested, so next time we'll meet, there will be 100 in such flight. Yeah. So what we did over the last 12 months, we divided the pipeline into 10 different things, which really sped up the process, because some of your observatories already have very good astrometry, so we can skip the number 1. Sometimes it even cuts in half the whole process. We developed some new routines for profile photometry. We restricted the data upload to BHTOM with the Python capability, and tomorrow I will show you how to do it, how to use that. And we began to prepare some documentation and to prepare some manuals. And now about the statistics for individual process files. So this only covers the last 6 months. We prepared the report for ORP in May, and we had total, we uploaded almost 16,500 files were uploaded. But after that, after the last 6 months, we are at almost 26,000. So the interest in our service is beginning to explode. And if you happen to see some errors on our webpage, this means that our server does not have the capability to cover all of the movement in the network. But we will change that probably this year. Yeah, and 2 more things. An example like from BHTOM. This one is Gaia 20 FNR, and it has almost 10,000 data points. And you can see here that it also has some data points from Swift in the bottom. There are some data points that were collected from open access surveys. And here's the closer look. One thing also already stands out, that you have this doubled, tripled, in some cases even quadrupled light course in the same filter. That basically means that there are different filter sets between observatories, as well as the standardization is not such straightforward. Sometimes the B filter will go to B, sometimes it will go to I, and this is also what we are working on right now. We have some questions from the users why this happens. Basically, it happens because our standardization routines are not perfect, but we are working on that as well. And here you have the clean data. So the microlensing event light curves looks very, very nice. It even has some bumps visible along the way. And here's in the left, in the brown, you can see also the light curve from test observatory. So we are collecting the data from many sources, and then designated person is going to analyze it. And now the last thing is an example observatory, and we chose REM for the reason that we had a lot of data from REM and processed it. So REM is a rapid eye mount, 60 centimeters, and has this great capability to observe transients and monitor in different bands at the same time. So simultaneous observations. It's very capable instrument, and can be triggered remotely. And we are now working on downloading the data from RAM automatically and processing them through BHTOM as well. Yeah, and here are some statistics from the objects that were already observed, so far observed with RAM. As you can see, some of the targets have nearly 100% of successfully processed files. That means that even though the weather is not reflected in those numbers, even the worst images can be processed successfully, and we can have some photometric points from such observations. There is one target, Gaia 20 AVM, that stands out from this table, and it's only less than 50%. Of course, there were only 60 files, so the higher the number goes, the statistic better, and the percentage goes up. But I can show you the difference between the two images for the same target. These are two different fields of view, two different weathers, two different focuses. Sometimes it happens that the pointing is bad, and 40 images are just not from the same object for the given object. So this is exactly the case why the percentage is so. But all in all, almost 95% of 60 centimeters multi-filter telescope have been processed successfully. Common sources of error are wrong field of view, as you saw, bad weather, a very high background, closest to moon, or prolonged exposure, problems with telescope, like pointing problems, out of focus, saturation of the detector, and so on. And of course, some user problems when somebody uploads data for, let's say, 20 FNR, but that was and new coming features, deleting selected data points from BHTOM, so the user can delete the points that they're not happy with or they have been uploaded wrongly. Many of you asked us about that, and we are currently developing the procedure to do that. We are testing custom object names. So for Staszek, it would be perfect to just put the name like Staszek's favorite star 1 and put the right extension and declination, and for us that would be sufficient. So custom object names. We are working on downloading new surveys, so to have more coverage over the wide wavelength area, and more scripting. So to trigger and to download and process observations automatically. All coming soon in BHTOM 2, which probably will be introduced in a little bit tomorrow by Mike. And I would like to thank these 7 people because they uploaded so much files that allowed me to correct my many mistakes. So many thanks to the deepest contributors to the uploading of that. That would be all. Please contact us if you have any questions. And please remember, if you put the slack.bhtom.space in your web browser, it will automatically redirect you to Slack, and you will be invited to join our channel. Yeah, that would be all. Thank you very much. Questions?
Okay, sorry, but we don't have time for questions. But
I will be available at the dinner.
Exactly. So we can meet during the dinner or after lunch tomorrow. And the last presentation is from Jakob from Berlin.
Hello, can you hear me?
Yeah, we hear you. And Jakob, please, if it's possible, try to not go further than 15-17 minutes, okay?
I will try.
Okay,
can you see my screen?
Right now, yes, we have.
Okay, great. Hi, everyone. Thanks for inviting me. I'm going to talk about the AMPEL platform. I'm sorry I can't be with you in person, but I'm still very happy to be able to share what we've been working with. First, to provide some setting for kind of what we see as the outlook for astronomy in general and for real-time astronomy in particular. And I think these are areas that we've all kind of gotten used to now, or aspects. The first is, of course, the very large data volumes that we will see in the coming decade or so, spanning across the wavelength ranges and across different messengers. And this leads to different kind of aspects or problems, or of course, possibilities. So we need to find tools for managing these large data volumes, which are certainly too large for us to handle them manually or in a one-by-one case. Kind of another aspect that comes together with that is provenance, and provenance can mean different things. And I here like to highlight two aspects related to that. One has to do with fair data. I think allowing science data products to be fairly distributed is something that we're all working towards now. In astronomy, we're pretty good at making things findable, but it's still very hard to make things interoperable and reusable. And these two aspects have a lot to do with provenance. Another fact that I think we have to acknowledge here can be mentioned or called green computing. So what do I mean with this? Well, the fact is that one reason we will not be able to store or process all the data volumes that we will be getting with future observational facilities is that we won't have the energy to save them all and to process them. So this will be some aspect of green computing that we will have to choose what we do with the data. And then we again need tools to figure out, so which of all the observations did we actually process and save, and what could we have missed? And then a third kind of related aspect has to do with software development and engineering. So this goes in hand with getting large data volumes and trying to keep track of what we did to it. And that's that we have to get better at writing software pipelines that can be reduced and understood. So there are now great tools for that in how to share software, how to make software modular, how to continuously help each other in improving this software. But this all means again that we need to have tools in which we can actually use this for astronomy. So this was what we set out kind of to at least do with AMPEL. So this is a modular platform. It's not designed for any specific individual science case, but rather as something which can process data, apply some sort of analysis schema to this, and then keep track of what was done at what point of time. So one mode of AMPEL is what's shown as a solid line in this figure. And that's what we typically in these days calls a broker, and that was already mentioned. So we have these huge data streams that are coming. A broker then applies some sort of filter to that and sends some output in real time to some sort of medium where this then selected output can be viewed and reacted to and so on. For example, by a TOM. But this is one of these uses that we have for AMPEL, but the input can just as well be simulated data and archives. It doesn't have to be real-time data, even though that's mainly what we've been using it so far. And kind of the way I like to summarize it is as code to data. What do I mean with that? Just a brief example. So the idea here is that in astronomy so far, we typically observed some data and then we sat down and analyzed that. Here it is instead, and the problem with that approach is that when we have huge data volumes, the idea of first downloading or getting all of the data won't be tenable anymore. So instead, we start with an ID, some sort of scientific hypothesis, which could be that some particular kind of transient exists, for example. Then we determine a likelihood or a test function or an algorithm for finding those. We test this on some sample data locally. And then once we've shown that it works on sample or simulated data, we then run this on a computing center on some real-time data stream or archive data. And this is what we've realized in AMPEL. You develop a unit, a Python module typically, and then you write an analysis schema that you can run locally, which basically tells this unit to process some set of input data file. And then once you have this analysis schema, you can upload this to a live instance. For example, we have one running, this is Soiten, which will then run this analysis unit on large sets of data. So I know that this is still abstract, so I'm just going to provide one example of current usage of AMPEL. This is mainly based on ZTF optical data, since that's the largest data stream we have right now. So early on, the TDE group in ZTF, so the group trying to find tidal disruptions, they defined a set of metrics for identifying likely TDE events. So for example, based on the rising time, the light curves, and the colors. And they then encoded that into an AMPEL unit. And since then, we have compared these metrics to every ZTF alert, and then in real time defined a small list of TDE candidates that they've been able to confirm. So in this process, I think they've managed to triple the amount of TDEs during the last few years of ZTF observations. In parallel, another multi-messenger group again used ZTF data, but instead looking for optical counterparts to multi-messenger alerts, so from IceCube or gravitational wave alerts from LIGO Virgo. And then they published lists of these potential counterparts, again identified through AMPEL. And then, of course, what was fun was that these two groups, in a surprise to everyone, could combine their output and actually find a new or find a potential source for the extragalactic neutrino flux seen by IceCube. So it now seems like TDEs might be a source of these. So this is the way that AMPEL works now, that you can kind of devise some metric or algorithm that you then apply to real-time data. And then you can analyze large sets of data in this way. So the main reason I wanted to listen in here and talk is for potential future interaction points. So we currently do not directly ingest Gaia alerts. They are in some sense too few, and we instead do an indirect comparison through the transient name server as that's coming out. But there are certainly lots of possibilities, especially the fact that there might be alerts going down another magnitude to 20th magnitude. And there we will see a lot of possibilities of detecting new events and combining these detections with data from other surveys. And then, of course, it doesn't matter if the false alarm rate is as low, because this will all be compared and computed in a large throughput facility. Other interesting things compared with ZTF would be to, in a consistent way, combine these surveys to do better astrometry also for fainter candidates. And then something that I just added based on the talk this morning was where we saw the deficiency of confirmation of spectroscopic follow-up of galactic Gaia alerts. So this would also be something where it seems like if we could identify the most interesting and relevant galactic alerts, so these would also be something that we should follow up more closely. A second set of interaction points we just looked at the black hole TOM. And this is, of course, another area where I think we can do much better. Can we find new smart ways of directing a real-time supply of maybe ZTF alerts now, but certainly Rubin alerts or LSST alerts coming up, both including optical counterparts, young transients. The figure to the right here shows a program we actually had through Opticon of doing robotic observations of very young transients without any human in the loop using the LCO network. So there we had a really nice, we have a really nice class of objects that were followed up within minutes of the first detection. And then, of course, we have also searched for unique transients like the gravitationally magnified or multiply magnified supernovae that we discovered a month or so ago. So in both of those areas, I would be very happy to talk further. Again, it's annoying that I can't be there, but again, we can talk now or later. The rest of this presentation is mainly a demo that I will not go through here, but those slides are going to be made available. Basically shows how you can, for example, implement an algorithm for finding fast declining optical events, develop and try that locally on your computer, and then apply that, for example, to a LIGO Virgo, a multi-messenger region or HEALPIX map, and then get the list of optical candidates, which, for example, you can feed into your TOM. Okay, I think that already brings me to my summary. So we need new tools to make use of the future very large real-time data streams. And AMPEL is one such tool. It's a public tool for executing analysis schema. An analysis schema, I didn't talk too much about them, but that's a very powerful tool. As I mentioned, they can be developed locally. They can be run on a computer center. They can also be shared in others, for example, in a publication to allow anyone to repeat your analysis, or for example, someone else to extend your analysis and improve it in some other ways. The next few lines show how you can install AMPEL locally and run a quick analysis schema looking for some fast declining events. And as I mentioned, we have a live instance running in DESY Soiten. So once you have configured analysis schema that you think are working well, then you can contact us to have it run on the full CTF alert stream. The final thing I wanted to mention is that we're working closely with the Helmholtz Weizmann Research School for Multi-Messenger Astronomy. And in there, we have a new round for applications for the PhD school. So many of the students will work with us. So if you have candidates, you can please direct them there. Thank you.
Thank you very much. Because Jakob is on Zoom, so any questions from lecture room? Do we have any chat?
Hi Jakob, this is Lukasz here. Very nice stuff. I'm very sorry that we couldn't make it here, but I hope we will have chances to talk more about this. So just to double check, this is the only stream which you handle so far is the ZTF one, right? And which is great, but what are your plans on expanding to different streams, or you're just waiting for LSST?
Other streams that we're working most closely with now are basically multi-messenger streams. So gravitational wave, neutrino, gamma rays, and so on. That integration is already, it's working, but not in a live instance, but we have many projects working with that. In terms of other optical data, we are set up to do it, but the ZTF stream is just convenient to work with. It's a little bit also driven by our user base needs. If there would be someone who would come to us and say, I would really like to have a combination of this data stream with the CTF data stream, then I think we would make that happen. At this stage, most of our users are kind of busy trying to use the ZTF data stream as well as they can.
Sure, that's of course ZTF is perfect for this, and it started the revolution. So we should all tune in.
But I think to take this even further, I think it will be, to do this even better, combining optical data streams would I mean, it was one of our intentions all the time to be aware of this. And for example, or to be able to do this. And for example, if there could be Gaia alerts going down to fainter magnitude, then that's definitely something that we would include, because that would then complement the ZTF depth very well, and would also be able to use the Gaia astrometry right away would I think allow for a lot of new science projects.
Okay, great. Thank you.
Simon, please. No, but come on. Give the question.
Jacob, thank you. This is Simon Hodgkin. That was a great talk. We should talk, because we do have a stream where there are hundreds per day that go down to 20.7. We call it the Gaia X detector. It's not public yet, but we could already start testing an interface to your system. And I'm really encouraged to hear that you can handle these large numbers and automatically do the overlap comparison in delta time, delta X space, I suppose, compared to ZTF. I think that would be.
Yeah, I think that would be great, and it will take a while for us to figure out the kinks. So I think it won't be public anytime soon anyway. So yes, we should talk.
Thank you very much, Jacob. If you have any more questions or want to discuss more, remember about Slack channels. Use the Slack. Always use the Slack, please. And now we have lunch break, but I would like to thank you. Thanks to all the speakers which we have in this first session. And after lunch, thank you very much. We're starting at 2:30 with the second session. So thank you for now. Przepraszam.